Okay. So in the previous lecture, we were having this discussion on thermodynamics, and we did a few things a few initial preliminaries regarding thermodynamics. Now let us start with another thing where we left our discussion. So I think everything is clear. One thing that we've already discussed so far. So I'll just recap you whatever we have discussed. Whatever we have discussed so far was regarding thermodynamics and its preliminaries. Preliminaries. So basically, what we've been able to discuss so far was system. We've discussed about boundary of the system, and we discussed that beyond this, there's something called a surrounding. Okay, we discussed different types of boundaries. We've also discussed that thermodynamics happens to be a phenomenological science because it is based on certain laws which uh, which are derived from our experiences. It is phenomenal science, and it derives its we derive most of the things from four empirical laws. Okay, so there are four laws. There are four laws that we are going to study from now on. So there is zeroth law, from which we will which is from which we will derive the definition for temperature, or which is sort of we get one of the quantities from zeroth law, that is the temperature. From the first law, we understand how energies uh, transact in a thermodynamic process. From second law, we're going to understand something called as entropy. And the third law establishes a limitation, a limitation on thermodynamic function, on thermodynamic function. So basically, that is since it is based on these four empirical laws, and these generalizations are made from experiences. That is, these laws need no certain proof. Therefore, thermodynamics is a phenomenological science. Further, we have also went through different other things, different small definitions like system, boundary, surrounding, etc. And I think we have discussed them in greater detail. In boundary also, we have discussed different kind of boundaries like adiabatic boundary, diathermal boundaries. System also we have discussed that also that we know that the boundary may be real or maybe imaginary also. System can be um, okay. Uh, system is something which we study. Like okay, basically this. So the thermodynamics system is something whose thermodynamics is under our consideration. So whose thermodynamics is under our consideration, that particular is called as a thermodynamic system. Um, it can be as small as possible, as large as possible. For example, you can take a beaker and you can have a water inside. This is also a thermodynamic system. Even as big as an ocean is also a thermodynamic system. Okay. Similarly, you can have real boundaries, imaginary boundaries. For example, you may have how should I explain? So, for example, you have this vial in which some reaction is going on. So let's say this is a test tube in which some reaction is going on. So basically this comprises of boundary. This is a real boundary here. But if you consider the problem of the ozone hole, if you remember, and you know that ozone hole is there in the stratosphere. Okay, this is also a thermodynamic system, but here the boundary is imaginary. Okay, it's imaginary boundary. Okay, so I think all these things we have understood so far. We have understood what is a heterogeneous system, what is a homogeneous system, what are macroscopic properties, what are microscopic properties. For example, we have this homogeneous system. For example, if I take test tube and just dissolve sugar into it, some sugar is poured and it is dissolved. So sugar in water, dissolved in water, or even salt in water. This will form what? This will form a homogeneous system. Okay. However, if you are taking an ice, now there are phase differences. This ice is a solid here. This is water here. Okay. So it contains of two heterogeneous systems separated by physical boundaries. Such systems are called as heterogeneous systems. Okay. Then we've already discussed what is a controlled. There are two types of things, that is controlled mass system, then there is a controlled volume system. One is called as a closed system, another one is called as an open system. So for closed system, is characterized by a controlled mass system. Okay, so here you can have an allowance for energy. Okay, you can allow energy to exchange from system and surrounding, but transfer of matter between the system and surrounding is not allowed. So transfer of energy, yes, is allowed, but otherwise it's not allowed. You can have both energy and mass or matter transfer, but volume is controlled. That is called as an open system. Okay, so basically, if the boundary of system is such that it allows the transfer of matter and energy between the system and the surroundings, then the system is called as an open system. But then there can be a closed, very typically closed system which does not allow matter, also does not allow energy to be exchanged between the system and the surroundings. Okay, so this system is called as an isolated system. And then we have seen something called as extensive and intensive variables. And we know that sometimes the properties depend upon the partition or subdivision of the system. For example, if you have a system and it gets subdivided into A1 and A2, and if now property is dependent on the subdivision or multiplication of the system. Multiplication of the system. So there are properties which are independent of subdivision, and then there are properties which are dependent on the subdivision or multiplication of the system. So in this way, we define two different properties. One is called as an intensive property, another is called as an extensive property. So if If the property remains the same, whether we divide it or not divide it, these are called as intensive properties. These are independent of subdivision and multiplication. And then there are properties which are dependent on it. These are called as extensive variables. And I have listed a few of them. And I've already told you that you need to really right now mug it up. And then we'll see in later discussions how these are. Important stuff that I already taught you was that intensive variables are independent of mass, while extensive variables are dependent on mass. Okay. One important property just for right now I'm writing. If F and G are two uh, arbitrary extensive variables, then you make a property which is F plus G. It will be that F plus G will be an extensive variable only. However, F divided by G or df upon dg will be an intensive variable. All these things we'll derive later on, but right now I'm just writing it for your sake. So for example, yesterday we did one of the extensive property was mass and volume. Both of them depend upon what? Subdivision. Both of them are extensive property, but their division, that is mass per unit volume, that is rho, is an intensive variable. Okay, I hope this everybody has got so far. These things we have already discussed. Okay. And then last, we started with thermodynamic process, if I remember correctly. The last topic that we were discussing was thermodynamic process only. Okay. Just give me a minute before I start today. Also, you have seen that thermodynamic system doesn't always imply that we will be discussing um, thermal systems. You might have seen that in the last class itself that I took examples from magnetism also. Okay, so it is not always necessary that we are going to talk of thermal systems. Okay, thermal is as in a gaseous system or something like that. But we may also discuss magnets. Okay, so we may also discuss magnets. Yeah, magnetism. So magnets can also be considered as a thermodynamical system. As thermodynamic system. And we had pressure and volume in gaseous system. Now, instead of pressure and volume, we have another variables. So pressure was an intensive variable. So another intensive variable here come as flux density, magnetic flux density, or you can also write it as magnetic field, external magnetic field also you can write. So magnetic field or magnetic flux density. And instead of volume, volume happens to be an extensive variable here in the gaseous system. This is an intensive variable. And here in thermodynamic system, when we consider magnets as a thermodynamic system, instead of um, volume, you have a magnetization here. And what is magnetization? I'll just write it here briefly. So magnetization is nothing but it is your total magnetic dipole moment per unit volume. So it is magnetic dipole moment per unit volume. And remember, volume is again an intensive variable. Okay, so you can have such systems also. Okay, so this is also that we have seen already. This is also something that we have seen already. Okay, just give me a minute. I think I'm audible right now. Okay, okay. Okay. Now see, having discussed all this, we'd also discuss thermodynamical processes. Today, let us discuss something called as a reversible process. Okay, reversible process, and can it really be realized? Can it be really realized? So let us discuss reversible process. Okay, so if a process is executed in a very slow and a controlled manner, in a very slow and controlled manner, such that or so that all the intermediate states, all the intermediate states between the initial and final, between the initial and final states, the final state, sorry, are in equilibrium. Are in equilibrium. And if necessary, the process may be executed back along the same equilibrium intermediate states, equilibrium same equilibrium state, that is these intermediate equilibrium state I'm talking of, from final to initial. Okay, so if a process is such that you can go from initial state to a final state, and all the states in between, I'm talking of all the states in between, they are of they are in equilibrium. All the intermediate states are in equilibrium. Only then we can say that the system is executing a reversible process. Otherwise the process is called as an irreversible process. One has to understand that the condition for reversibility is that each state which occurs between the initial and final must be at equilibrium. Okay. Otherwise, if this condition is not satisfied, then the system is said to be in irreversible process. Okay. Now, always remember that a reversible process can never be realized in practice. So, reversible process is an ideal concept. It is an ideal concept. Okay. And it cannot be realized in practice. It cannot be realized in practice. Okay. It cannot be realized in practice. This is something that you have to remember, and this is something that I'm going to derive for you. Okay. So for just to derive it, I'm going to take an instance Suppose a cylinder is there. Suppose there is a cylinder containing gas fitted with a piston. So fitted with a piston, you have this cylinder which contains a gas. So basically, I have a piston here supported by a weight. So basically, let us say this is your weight W, and this is your gas. Let me mark it as A and B. Okay. Now suppose if I remove this weight, then system will come to a state which is, let's say, A dash B dash. Let's say this is your initial state, and all of a sudden if I remove weight, then the state is A dash B dash. Okay, let us say this is your final state. Now if I'm saying that I have to execute a reversible process, then this reversible process has to be executed in a very slow and controlled manner, in such a way that each of the state between the initial and the final remains in equilibrium. So all these intermediate states between initial and final must remain at equilibrium, must remain at equilibrium. Okay. So what I'll do something new to you. So let's say again, instead of W, I'm taking the same volume. Instead of W, now let's say I have W by 2 and W by 2. I have two weights. I have placed two weights. Let us say W by 2 and W by 2. Now, if I remove one of the weights, if I remove one weight, that is W by 2, I will achieve this particular AB, this gas will uh, exert a pressure on the piston, and this will come to a midway. So basically now, after removal of one of the weights, that is W by 2, I can achieve one of the intermediate state midway between the two, that is CD. So this is your initial state AB, and this can be your final state. I've already written A dash B dash. So by removal of one of the weights, what has happened? You have achieved one of the intermediate state. So if I just remove one of the weight, I have achieved an intermediate state CD. Okay. Now, for instance, if I take W by 3 and W by 3 instead of W by 2 and W by 2, on removal of two weights, subsequently, I can achieve two intermediate equilibrium state. I can achieve two intermediate equilibrium states. Okay. But you understand that there are many states in between. There are many states in between. So instead of this, I can take W by N, W by N, W by N, W by N, and in totality N weights. Instead of W by 2, I can take W by 3, W by W by 3. So I can take three weights. It will comprise of W only, totality. Here also in totality, I have W by N, W by N, W by N. I have N weights. So in totality, I have this W weight only. Now, if I remove these N minus 1 weights, what I can do? I can achieve what? I can achieve N minus 1 intermediate equilibrium states. N minus 1 states, intermediate states at equilibrium. I can achieve this. Then how many intermediate states are possible? So this is a continuum. So there are infinite possible intermediate state, infinite. There are infinite states which are possible. Since this is a continuum. Okay. So between any two states, however small, there again exists another intermediate state which can be achieved. So basically, I will have to divide this entire place from AB to A dash B dash into infinitely small states. So basically what I have to do in order to execute, in order to tell that my process is reversible, I have to break it in many states. And these many states are how many states? How many states are possible in between? Between, let's say, this and this, these are two equilibrium states. Between this also, then there is an equilibrium state. So I can how many states I can achieve from here if I want to? I have to achieve in theory, I have to achieve infinite possible states. Can I achieve that in practice? No, because in order to achieve all these possible states, I must have infinite number of weights. And therefore, this brings us to a problem of irreversibility. So clearly, reversible process can only be idealized. It cannot be achieved in practice. It cannot be achieved in practice. This is first thing that you should understand. It cannot be achieved in practice. Okay. Another example is simple pendulum. So if I take a simple pendulum, let's say my initial position is A, and now it swings back to another position B. So when the pendulum bob swings from A to B, when it swings from A to B and again back to A, there will be some change in the temperature of the surroundings. Why? Because of the air resistance. Okay, so my pendulum bob would collide with the air molecules, and because of this air resistance, there would be some change in the temperature of the surroundings. Okay, and basically what will happen because of this air resistance, this entire process, I will claim that this will become an irreversible process, not a reversible process, because of this air drag. Now, what is the way to make it a reversible process? I can put it into a vacuum. But can a perfect vacuum be achieved? Answer is no. Can a perfect vacuum be achieved? There would always be some precision up to which a vacuum can be achieved. So can a perfect vacuum be achieved? Answer is no. So therefore, experimentally also you can understand here. The first one was a thought experiment. Here I have given you another experiment. So always remember, reversible process can only be idealized. It can never be achieved in practice. The main important point that you should remember is the system can be restored back to its initial position. For example, let's say it started with A and ended with B and it came to B and again came back to A. In this entire process also, there was in one loop itself. In one loop itself, it came back to B, it came back to A. Obviously, after a while, because of the air friction, it will dampen, it will stop. But in the first loop itself, it came back to A. But there was a change in the temperature of the surrounding. Okay. So no doubt, system may have restored back to its initial position, but this restoration is only possible by some change in the surrounding. Such processes are called as the irreversible process. So I'm just writing it for you. A system can be restored to its initial state only by spending some energy. Okay, can be restored to its initial state both by either by a reversible or an irreversible process, either by a reversible or an irreversible process. But for reversible process, process, this restoration to what? To the initial position. This restoration is made without any change in the surroundings. Any change in the surroundings. However, for irreversible process, as you've seen, there would be some change in the surroundings. Only then, and means restoration back to its initial position will accompany some change in the surroundings. Okay, now problem is that if system is not at equilibrium, so there must be some fluctuation. If there are some fluctuation, then such process cannot be represented by a path. So if I'm talking of irreversible process, then it cannot be represented by a path. And if you remember, yesterday I draw a path for you that if I'm saying that a thermodynamic process is being executed, the graphical representation of such thermodynamic system is called as a path. So if all the intermediate states are not at equilibrium, then such process is called as an irreversible process, and then it cannot be represented by a path. So what is the way ahead? And we already know that no process remains to be reversible in nature. Every process is irreversible process. Okay, because in order to achieve reversibility, it can only be idealized. It can never be achieved in perfect practice. So that we have seen already. Are you getting my point? Let's say if I want to really make some understanding out of it, how can I achieve it? I can only achieve it by uh, by uh, by executing that particular process in a very slow and controlled manner. Then also I cannot achieve it completely. Okay, then also I cannot achieve it completely. For example, just for an example, I'm explaining how reversibility can be in practice, how it can be achieved in practice. Again, perfect reversibility is not possible. Perfect reversibility is not possible. So in practice, how can we achieve? We can achieve it by executing a thermodynamic process in a very slow and controlled manner. In a very slow and controlled manner. So in a very slow and controlled manner, each process, each intermediate process will deviate. In practice, I'm saying, in practice, each intermediate state will deviate only slightly, only slightly from the equilibrium state. Only slightly from the equilibrium state. Okay, so each state is exactly not at equilibrium, but only slight deviately from the equilibrium state. Such process is called as a quasi-static process. Such process is a quasi-static process. So such process are a perfect, or you can say good approximation to a reversible process. Good approximation. Reversible process. always remember that a static process is just a approximation approximation to a reversible process. In general, actual processes are non-quasi-static because during the process itself, there always exists some very finite difference of pressure, temperature between the several part of the system. So basically, I cannot again consider it to be happening in practice, but uh, in order to achieve uh, the level best reversibility, what I can do, I can execute my process in a manner that all the steps in between, all the intermediate changes are just infinitesimally small, different from the equilibrium state. Okay, then I can say that my process is can be approximated to a reversible process. So in that scenario, this is called as your quasi-static process. This is called as your quasi-static process. How should I explain it? Okay, so I hope this is clear to you. Now let us move to another important concept called as indicator diagram. Okay, I hope this is understandable. If you're not able to understand, how should I explain? I'm just thinking about that. What you can do is, okay, before understanding indicator diagram, let us understand what I wanted to say. So basically, what I wanted to say, let us say, uh, again, let us take an example of piston only. So this is your cylinder. Okay, this is your cylinder. Let's say it is given with the given a piston. Okay, and this piston is massless. Okay, so don't consider any mass, and consider a massless and a frictionless, so that you don't have any losses. This is a frictionless uh, and massless piston. Okay, and let us say we have now 1000 kg of mass placed over it. 1000, okay, not kg, I should say 1000, 1 kg, let's say 1 kg, let's say 1000 grams. Okay, so let's say we place a 1 kg mass over it, and instead of 1 kg, you just realize it in this fashion. Like I was telling you, the W by N, W by N, W N kind of thing. So instead of W by N, you just think that there are 1000 masses here. If I'm placing, instead of this, I'm placing 1000 masses of 1 gram each. 1 gram each. You can take 10,000 masses of zero point 0.1 gram each. Then it will be all the better. It will achieve all the better. What you can say, um, reversibility. So because of placement of these masses, obviously it is going to go a little on the lower side. So this piston will move on the lower side. So if this is a cylinder, because of these masses, this will push down. So piston will push down. No, not piston. Piston will move down. And now, if you want to achieve the final state again, initial state again. So this is your final state and it is your initial state. Now, in order to achieve it reversibly, what you want all the intermediate states to be in equilibrium. You want all the intermediate states to be in equilibrium. So for that, what I've done, I've taken 1000 grams, 1000 masses of 1 gram each. So that uh, uh, I'll remove 1 gram mass each, 1 gram mass each. So if I remove 1 gram mass, the piston would, what will happen? Now pressure would slightly decrease and there would be slight expansion. So because of 1 gram mass, if I'm taking off from here, there are 1000 masses. If I just take one up, what will happen? There will be slight decrease in the pressure, let's say dP1, and there will be slight expansion in the volume, let's say dV1. So now, if let's say let's say this was, instead of writing final, let's say this is your initial position, you want to get back to your final position. Let's say here we start our problem from here. Our initial pressure was, let's say P1, V1, and let us keep it at a thermostat. So basically we don't want our temperature to vary. Let us keep it at thermostat. So basically we want our temperature to be constant. Now on removal of 1 gram, some decrease in pressure would be observed. So P1 minus dP1 and expansion V1 plus dP1. So what has happened? There is only slight change from the equilibrium state. There is only slight change from the equilibrium state. Slight change. Because there is a slight change in the equilibrium, there is some work done. So there is some work done in the surrounding. So obviously this will generate some work done in the surroundings, dW. But this is in principle small. So such process are a good approximation to reversible process. And if I'll start removing one by one, so 1000 steps I can take this process and I can reach to the final process. This is a good approximation to a reversible process where I'm just deviating from the equilibrium state by an in principle small variation. Okay, in order to achieve all the more, ideally you can by the way put sand of 1 kg and start removing one particle of sand. Your life will entirely, you will die in just lifting this entire piston away. So the point is, what I want to say is that all the real processes are irreversible only. You can only think of something called as a quasi-static process theoretically, and those quasi-static processes are nothing but they are good approximation to the reversible process in which all the intermediate state will deviate only slightly, very infinitesimally small from the equilibrium state. Okay, I hope now I have made the point very clear. If still there is doubt, please let me know. Now let us move to something called as an indicator diagram, which we have drawn quite often in our standard 12th also, but just for an example, I'm drawing it for you. So the stages of quasi-static process are what? So they are just stages of quasi-static process are nothing but a series of almost or approximately equilibrium state. Equilibrium states and all these small deviating equilibrium states or approximate equilibrium state are represented or indicated. They are indicated by a series of points in the xy plane. Series of points in the xy plane. Okay, and these x and y are nothing but the thermodynamical variables, and this kind of representation is called as an indicator diagram. This kind of representation is called as an indicator diagram. So let us discuss some of the quasi-static thermal processes that you have already studied in your standard 12th. So some quasi-static process you've already understood or learned in your school level physics. One is called as an isothermal process. So what is an isothermal process? Isothermal process is one in which your temperature of the system is kept as constant. So for example, if you allow your gas to expand at a constant temperature, let's say the previous case. So in this, the temperature is constant, and if you are seeking an ideal, if you are doing it on an ideal gas, so basically this will become a constant. So P is inversely proportional to volume. If P is inversely proportional to volume, then the trajectory, then the graph of P versus V will resemble a rectangular hyperbola. Okay, so this is your indicator diagram. Okay, the same thing I can draw if the process is isothermal. Then let's say temperature is here, volume is here. Then temperature constant implies this, and if I draw it in terms of P and T, then pressure is here, temperature is here. If temperature is constant, then this is how I can draw an indicator diagram. Okay, if the process is isobaric, it implies what? If I'm talking of isobaric process, it implies that pressure is constant. And if pressure is constant, it implies what? If I have to make a P versus V graph for it, okay, so if a process is taking place at a constant pressure, then that process is called as an isobaric process. And if I have to make a indicator diagram P versus V, it will be simply, if I want to make a graph of V versus T, it will be a straight line, because pressure, this is how it is. If I'm taking pressure to be constant, then volume is directly proportional to temperature, and it will give me a linear relationship. So there would be a linear graph. And if I'm drawing a graph of P versus T, so again, it will be a straight line. Okay, and if I'm talking of something called as isochoric process, where volume is constant, so in that scenario, my P versus V graph will look like this, or I can say indicator diagram here. If I want to draw a V versus T graph, it will be simply this. And if I have to draw something like P versus T, if I draw P versus T, it will be a linear graph. So I hope this is clear. So these are like indicator diagrams. All of these things you already know. I'm not going to spend much time here. Okay. Now, there is a relations which are called as a transitive relation. That is, if A is related to B, B is related to C, then A is related to C. Such transitivity is also seen in thermodynamics. This mathematical transitivity is seen in thermodynamics as well, and this is encapsulated in the form of zeroth law of thermodynamics. And as I told, the theme that gives this zeroth law of thermodynamics is temperature. Okay, so basically the core is temperature here. So I've already told you, just keep in mind zeroth law, temperature. How temperature? I'll let you know, don't worry. First law, energy, is an expression of energy. Second law, the key term is entropy. And the third law explains consequence, or you can say a limitation, which is kept on the thermodynamical variables. So what does zeroth law of thermodynamics states? It is, as I told you, if A is related to B, B is related to C, then A is related to C. If you keep this in mind, this is a kind of law. So basically, if two systems, if I'm writing if two systems, A1 and A2 are in thermal equilibrium, are in thermal equilibrium independently, with the third system, A3, then A1 and A2 are also in thermal equilibrium. And how do you quantify a thermal equilibrium? By the constancy of temperature. So if two bodies are in equilibrium, thermal equilibrium, let's say A and B are in thermal equilibrium, then their temperatures must be constant. So that is why I told you the zeroth law of thermodynamics is related to temperature. Okay, if two systems, A1 and A2, are in thermal equilibrium independently with the third system, A3, then A1 and A2 are also in the thermal equilibrium. For example, I make it so that you can understand. So let us say if I'm making a graph here, not a graph, basically I'm trying to represent it. Let's say this is your A3, and A3 is linked to A1 and A2, and A1 and A2 are separated by an adiabatic boundary. Let's say this is separated by an adiabatic boundary, and this is your diathermal boundary. So this is your diathermal boundary. So your A1 is in thermal contact with A3, A1 is in thermal contact with A3, A2 is in thermal contact with A3. And if it is at equilibrium, it implies that TA1 is equal to TA3. And from here, the temperature of A2 is equal to temperature of A3. So transitively, from the transitivity, we already know that TA1 is will be equals to TA2. So this is a kind of mathematical relation that we already know. That transitivity in the mathematical relation from that is a similar kind of approach here. So if A1 is in thermal equilibrium with A3, A2 is in thermal equilibrium with A3, then A1 and A2, which here are separated by adiabatic boundary, they are also actually at the same temperatures only. So basically, here I'm showing you they're separated by adiabatic boundary, but uh, but if according to zeroth law, if I'm keeping this system, then temperature of A1 and temperature of A2 also becomes the same. So basically, if I'm saying that A1 and A3 are in thermal equilibrium with each other, A2 and A3 are in thermal equilibrium with each other, then A1 and A2 are also thermal equilibrium are at thermal equilibrium with each other. So remember, all bodies in thermal equilibrium must have a common property. Must have a common property. And what that common property is, I've already told you that common property is your temperature. That common property is temperature. So temperature decides whether uh, whether one body is in thermal equilibrium with another body or not. So if one body is in thermal equilibrium with another body, then they are at the um, they're at the same temperature. If they are at the one body is in thermal equilibrium to the another body, then both of them are at the same temperature. I hope it is clear. So now, this from here we'll come to another important thing, that is equation of state. Okay. So what happens is in let's say if I'm talking of gaseous system, pressure, volume, temperature. So what I can do, I can express one of the quantities as a function of the other two. So if I want to express my temperature, I can express my temperature as a function of another two quantities, that is pressure and volume. Okay. So what I want to say that if I'm saying that my gaseous system is there, so it will be a function of PV and T. Here I can express my temperature. For instance, you can do another one also. For example, temperature can be expressed as a function of pressure and volume also. Okay. So such representation, we say that we are talking of something called as an equation of state. We are talking of something called as an equation of state. For example, for ideal gas, I can write PV is equal to nRT, or simply RT if number of moles is equal to 1. So temperature can be expressed from pressure and volume. Once I know pressure and volume, I know everything about the state of the system. So if I want to gauge what is the state of the system, what I need to know, I need to know only, if I want to gauge what is the temperature of the system, what I need to know, I only need to know my pressure and volume. If I know my pressure and volume, I can know the state. So therefore, this is called as an equation of state. This is called as an equation of state. I will write it here. Several other equations of state also. Okay, one process I forgot. One process is called as a cyclic process. Just write it here. Actually, isobaric, isochoric, I already written. Simple. I think this again you have studied in your 12th class. So if the transformation of the system is such that if the and I'll come back to the equation of state also. If the transformation of the system is such that it returns to its original state, covering any path, then it is called as a cyclic process. Then this is called as a cyclic process. So we'll come to all these things, but just right now, in sense of definition, I'm saying. I'll talk of some mathematics also before moving forward. But I hope everything is now clear regards isobaric, isochoric, regards all these things. Okay, this we have done. Now let us move back again to the equation of state topic only. So equation of state. So equation of state, I have already expressed that. Let us say if I'm talking of a gas, we need three variables, that is pressure, volume, temperature, and one of the things, let's say here temperature, can be expressed as a function of another two. So if I want to express pressure, I can express it in the terms of volume and temperature. If I want to express temperature, I can express in terms of pressure and volume. So what does equation of state allow? Equation of state allows us to express one of the variables. By the way, these are also called as the state variables because they represents the state. So I'm writing equation of state allows EOS. Equation of state allows us to express one of the state variables, one of the state variables as a function of the other two, as the function of other two. So this is what an equation of state does. So for example, I told you, if I'm saying of the if I'm saying that uh, what you can say, if I'm talking of something called as ideal gas, then the equation of state remains PV is equal to nRT, or simply PV equal to RT if I'm taking number of moles in the system to be 1. If I'm talking of if I'm talking of what, if I'm talking of ideal gas instead of ideal gas, if I'm talking of real gas, then this will become A plus P upon V square times V minus B is equal to RT. Here are some constants. If I'm talking of a paramagnetic solid, then the equation will have magnetization, magnetic flux density, temperature. Then magnetization can be expressed as constant times magnetic field upon temperature. So here magnetization is related to magnetic field as well as temperature. You know magnetic field and temperature, you can know the magnetization. Okay. If you're talking of a stretched wire, so if I'm talking of a stretched wire, and due to the tension in the wire, there is some increase in the temperature, then it can be expressed as a function of length, tension, that is expressed by force F, and temperature, which is T. It is, so I can write my length at any point as L is equal to L naught. L naught is initial length plus some constant times tension force. This is your tension force. Then you can write another constant times T minus T naught. T naught is initial temperature. So this is how I can express my length. So for a stretch wire, my thermodynamical variables will be length, function, length, tension, and temperature. And equation state will be this. So from one of the from two of the variables, you can know the another variable. From two of the variables, you can know another variable. Now, you may have studied a few material properties and what you can say, a few terms I'm going to write here. So if I'm talking of the gaseous system, so if I'm talking of a gaseous system, gaseous is characterized by what? Pressure, volume, and temperature. It can be characterized by pressure, volume, and temperature. First derivative, I'm just writing here. First derivative of PVT with respect to each other means pressure with respect to volume, volume with respect to temperature. All those things I'm writing. First derivative of pressure, volume, and temperature are used with respect to each other. With respect to each other uh, are instrumental in defining three material properties. And these are what I should write, uh, coefficients of coefficient of thermal expansion, coefficient of thermal expansion, thermal tension, and coefficient of isothermal compressibility. This is expressed as alpha, coefficient of thermal tension. This is denoted by beta. And then there is isothermal compressibility, coefficient of isothermal compressibility, which is denoted by kappa. Okay. For instance, this compressibility is what? I'm just defining one of them. You know already from your high school physics, so I'm not writing it as much. So compressibility measures what? Compressibility measures fractional change in measures fractional change in volume of gas due to increase in pressure. Due to increase in pressure. And obviously, if I'm increasing the pressure, volume would be decreasing. So I write it as dV upon dP, and then I just write a negative sign also. Okay. So how do I define isothermal compressibility? Coefficient of isothermal compressibility, it is minus one upon V del V upon del P at constant temperature. Okay. So if you remember your bulk modulus, if you remember your undergraduate class, like undergraduate class where you studied all these modulus of rigidity and all those things, there uh, you may have come across this kind of term which is called as a coefficient of isothermal compressibility. So coefficient of isothermal compressibility is given by minus 1 upon V del V upon del P. And you know this minus comes because you know that if I'm increasing pressure, my volume would decrease. And if my volume is increasing, then there would be increase in pressure. So these are, therefore, I keep a negative sign here. Okay, now another one is coefficient of thermal expansion. Okay, and you understand all these material properties are what? These material properties, coefficient thermal expansion, coefficient thermal tension, coefficient of isothermal compressibility, they're mathematically obtained how? They're mathematically obtained by keeping one of the constants. So for example, I'm keeping one of the parameters constant, and I'm checking how what would be a thermodynamic response if I'm changing by keeping one of the thermodynamical variable constant. Okay, so this is coefficient of isothermal compressibility. How is alpha defined? Alpha, which is your coefficient of, I think, thermal expansion, it is defined as 1 upon V del V upon del T at constant, I think, pressure. If I'm not wrong, please see all these terms. If I'm wrong, please do tell me. It is 1 upon P. I think this is del P upon del T then. At a constant. Okay, in general, these are not constants. Okay, in general, I'm writing. These are not constants, but vary from place to place on equilibrium manifold. Okay. Now we'll develop some relationship between all those three things. So let us see how. And this will be today's topic, which is the deductions from the what we can deduce from these equation of state in general. So what we can make some deductions from general equation of state. Generally, what we can deduce from equation of state. So as I mentioned, what is an equation of state? Because from equation of state, what we can say, we can express one variable, one state variable as a function of another two state variables. So for example, I can express my volume as a function of both pressure and temperature. I can write my volume as a function of both pressure and temperature. So if I take the differential of V, that is differential dV, okay, this represents what? It represents the difference between the two equilibrium intermediate states. Okay, so difference between the two neighboring equilibrium states. Difference in the volume, okay, difference in the volume between two neighboring equilibrium states is given by dV. So dV is what? dV I can write as del V upon. Okay, before moving further, I'll just write a mathematical preliminary right now for you, so that you know that, and I think you know it from your multivariable calculus. If you don't know, I'm just writing it right now here. Just writing it for your sake. Just writing it here. So if you are having a differential function, so given a differentiable function, given a differentiable function of two variables, let's say I'm talking of sigma as a function of x and y, then its differential, and we'll talk of something called as perfect differentials or exact differential, inexact differential, but right now just I'm talking of its differential d sigma can be written as del sigma by del x times dx plus del sigma upon del y times dy. So this is how I represent a change or a differential of one of the differential of a dependent variable, which is dependent on two of the variables. So if you have two variables, let's say x and y, and if I want to write the change in sigma, so that is d sigma would be equals to del sigma upon del x times dx plus del sigma by del y times dy. Okay, so we'll come on to some course mathematics later on, but right now, let us make some deductions from the general equation of state. Again, coming to back to the topic. So if I have volume, volume can be expressed as a function of both pressure and temperature. Volume can be expressed as a function of both pressure and temperature. So dV can be written as del V upon del P times dP plus del V upon del T times dt. Okay, and it is a norm in normal in this is a kind of, you can say, notation in thermodynamics, that what we do, if I'm writing a partial derivative, let's say del v upon del p, it implies necessarily that if I'm differentiating with respect to p, the temperature has to be kept constant, but we write it here, that is at a constant temperature. If I'm writing del v upon del t, it implies I'm talking of constant pressure here. If I write what is dp, so what would be a dp? dp would be del v upon sorry, P would be function of both volume and temperature. It will be function of both volume and temperature. So sorry. Okay, I hope it is clear. So it will be function of both volume. Pressure would be function of both volume and temperature. So if I write del P, dP, sorry, dP will be del V upon, sorry, del P upon del V at a constant temperature times dV. And what I can do, I can write this as equation number one. I can write this as an equation number two, and I can replace, instead of dP, this particular thing. So here I can replace this, instead of dP, I can replace this. So what I'll get, I will simply get 1 minus, if I replace, you just replace it on your own, you'll get del V upon del P at a constant temperature, then del P upon del V at a constant temperature times dV, minus del V upon del T at a constant pressure, plus del V upon del P at constant temperature, del P del T a constant volume, and then this is dt equals to 0. Okay. Now, what does this general equation of state gives me? What does this general equation of state give me? So there are certain relations that we are going to develop from this we can deduce from this general equation of state. Let us see what. So if there are two states which are at the same temperature, then the dt would be 0 for them. And if dt is 0, then what I'll get? I'll simply get del V, del P at constant temperature is equals to 1 upon del P, del V at a constant temperature. If I write dt is equal to 0, then I get this. What does imply? It implies that we have obtained a mathematical relation. We have obtained a mathematical relationship, I should write, which allows us to replace. So instead of dt, you can also do this thing. If you place dv is equal to 0, okay, and if you place dp also equal to 0. So what will you obtain? You will obtain a mathematical relation which allows us to replace any partial derivative. PD means partial derivative, by the reciprocal of the inverted inverted derivative with the same variables. with the reciprocal of inverted derivative. So basically inverted derivative means del V upon del T. Now here it is del P upon del V with the same variables. Okay, is that fine? Okay, keeping the other one constant. So keeping temperature constant. So what you can write, so from here I can write, from here what I can get, if I t dt is equal to 0, I'll get this del V upon del P at a constant temperature is equal to 1 upon del P upon del P upon del V at a constant temperature. So this is reduction number 3. Similarly, I'm keeping it to you only, that if I put in this particular expression, let's say I name it as 3, equation number 3, let's say this is equation number 4. Now in equation number 3, I've already placed dt equal to 0. Now instead of dt, if I place dv is equal to 0, and let's say let us keep dt non-zero, what I will get? I will simply get del v upon del t at constant pressure is equals to negative of del v upon del p at constant temperature and del p upon, no, so sorry, del T at constant volume. And from this equation of state, we already know that if I want to express del V upon del P at constant temperature, I can always write it as 1 upon del P upon del V. Similarly, what I can do, I can write del V upon del T at constant pressure as 1 upon del T upon del V at constant pressure. This can be written from equation of state. So if I use this kind of relation, I'll get what? Minus of del V upon del P at constant temperature, del P upon del T at constant volume, and del T upon del V at constant pressure is equal to 1. Or in other words, I can write it as del V upon del P at constant temperature, del P upon del T at constant volume, and del T upon del V at constant pressure is equals to minus of 1. I hope it is clear. Okay, I hope it is clear. Okay, so here we have obtained an important relation that you have to really remember. This is an important thing that may be asked in examination or otherwise also. This is an important thing that you should really take care of. Okay, now what you can do is, how should I explain? So you already know. So important things, I will just list here what you have obtained so far. So point number 1, what you have obtained from general equation of state, you have obtained one very important thing. That is, if I want to write what? If I want to write, let's say del V upon del P at constant temperature, then I can write it as del P upon, sorry, I can write it as 1 upon del P upon del V at constant temperature. I can also write del P upon del V at constant temperature is equals to, okay, sorry, del V, I should write better. I'm so sorry. Just give me a minute. Eraser. I should just write in a different way. So if I want to write, so sorry. If I want to write del V upon del T at a constant pressure, I can write it as 1 upon del T upon del V at a constant pressure. And if I want to write third, del P upon del T at a constant volume, then it is 1 upon del T upon del P at a constant volume. Is that fine? These three things you can always obtain from the general equation of state. And another thing that you can obtain, number 4, was, I think I've already stated, I've already written. It is equals to del P at a constant temperature, then del T at a constant volume, and del T by del V at constant pressure. All these are equals to -1. You already know another thing, that is alpha is given by 1 upon V del V upon del T at constant pressure. What is your beta? Beta is written as 1 upon P. This is coefficient of thermal tension. I think this is del P by del T at a constant volume. And what is kappa? The coefficient of thermal compressibility, it is -1. I think -1 upon V del V upon del P at a constant temperature. Okay. Now from all these expression, if I try to make some sense, let's say, if I try to make some sense, okay. So these are the things that we have already derived. And from all these, if I want to make some sense, I'm leaving this as your homework. Try to establish, a relation which is given by pressure times beta into kT is equals to alpha. Okay. So try to write this expression, try to obtain this expression using these equations. If you are unable to do it, I will again this relation explain this relation in the next class. And from next class, we are going to start with something called as the first law of thermodynamics. Till then, take care. Bye.